Well students, today we will see a new topic, atomic spectra. So you must be seeing this human DNA or the fingerprint is an identity of a person, right? So if the fingerprint of mine will be always mine, it cannot be the same of another person, right? Similarly, even the atomic gas has got a fingerprint. So how do we find that? So we have atomic spectra for that. So first let's see about this emission spectra. How do we get this emission spectra, or what is this emission spectra? See this, emission spectra will be obtained when you take a gas, atomic gas, and you pass electricity through it. Okay? When electricity is passed through atomic gas, you obtain, see, bright lines in the dark background. Okay? You will be going to see kind of bright lines in the dark background, which is known as emission spectra. Okay. So this spectrum has got a speciality. Okay, it contains specific wavelengths only. It doesn't have all the wavelengths. It's not a continuous spectrum. Okay, it will contain only specific wavelengths. And you can see this, I've written here, it is a fingerprint of a gas. So if I take hydrogen gas, okay, the spectrum whatever we get from this hydrogen gas will not be same as that of a helium gas. Okay, it is the spectrum which is specified to this hydrogen gas alone. Okay, that's the reason why we call it as a fingerprint of the gas. Okay, we have another type of spectrum which is absorption spectrum. This absorption spectrum can be obtained when we pass white light through a gas. Okay, an atomic gas is taken and we pass white light through there. Then we obtain some kind of dark lines in the white bright background. Okay, that is known as absorption spectrum. So these are the two type of spectrum which may be asked for 1 or 2 marks. Okay, maybe a 1 mark question. So you can see here in the diagram, see, you should excuse me for the clarity of the diagram, okay, because you can refer your textbook and you can get the clear picture of that. So you see here, the spectrum of wavelength is taken, okay. So you can see here, this is 1875 nanometer, see, nanometer, okay. From this 1875 to 820, we have a series of spectrum called Pasteur series. Okay, from 1875 nanometer to 820 nanometer, we have a series called Pasteur series. Then we will consider from here 656 nanometer to 365 nanometer, we have something called the spectrum of Balmer series. Okay, this is spectrum of Balmer series from 656 to 365. Okay, then what we have is from 122 to 91, which is Lyman series. So this is actually the picture of atomic spectra. So you can see all these are lines. See, we call the bright lines, right? So these are the bright lines on the dark background. If you search in Google, you can get the clear picture, the original picture of these spectrums. So that will give you more idea. Okay. Now we will study a bit detail about this spectral lines. Okay. We will be considering only Balmer series. The reason why Balmer series considered, because you can see the wavelength range. What is the range of wavelength? It is from 656 to 365. You know what is the range of visible spectrum? Visible spectrum is nearly from 400 nanometer to 700 nanometer. So you can see this Balmer series which is in the visible range of spectrum. Okay, that's the reason why we give some more importance to this Balmer series. And you can see here, see I have written over here VIBGYO. You will come to know why. So let me take the first wavelength, which is 656. Okay, this is called as H alpha. We call this wavelength 656 as H alpha. Okay, and it is in the red region. See, it is in the red region. You can see here. See, lambda is less over here, lambda is more over here. What about frequency? Frequency, we'll write nu. So nu is greater over here, it is lesser over here. It is in the increasing order of wavelength, right? So red has got longest wavelength. So I'll take this. H alpha is named as, lambda, which is having 656.3 nanometer in the Balmer series, is named as H alpha. Okay, it is called H alpha and it is in the red region and it is having longest wavelength in the Balmer series. Okay, coming to next. See this. H beta. Okay, wavelength 486.1 nanometer, which is known as H beta, and it is in the blue-green region. See this? Blue-green region. So it may be the middle of the visible spectrum. So see this. What is the range? 486 nanometer. Okay. So this wavelength, what I have given is not the exact one, it is an approximate one, but we usually consider for the visible spectrum. Okay. So next one again, lambda with the 434.1 nanometer, which is known as H gamma. Okay. It is in the violet region. See here, it is in the violet region. And next it goes on like lambda, which is 410.2 nanometer, which is known as H delta. Okay, and lambda with the 364.6 nanometer, which is known as H infinity. Okay, so this H infinity is a series limit of this Balmer series. Okay, it has got shortest lambda and the series limit. You can observe something from this diagram. Okay, as wavelength decreases, see, as wavelength decreases, what do you see this? What is the spacing between the spectral lines? See, as the wavelength goes on decreases, the spacing between the spectral line goes on decreases. Correct, right? See, it was this much, then it came this much, again it goes on decreases. So just refer your textbook so that you will have a better idea of the diagram. Okay. Then what happens? Intensity also goes on decreases. So I may not be able to make it clear in this diagram. So you can just go through the textbook. Okay. Or you can just Google it. That would be a better thing. So you will see this will have brightest intensity. Okay. It will have the highest intensity. Intensity goes on decreases as the wavelength goes on decreases. Okay. So this is all about the spectral series. Okay. Now we will move on to a formula which is it's a simple empirical formula developed by Balmer. Okay. And what he says that the 1 by lambda, it is usually known as wave number. Okay. So 1 by lambda, that is equal to R into 1 divided by 2 square minus 1 divided by n square. And why this 2 square and n square? You will get to know that idea properly as we just proceed over the next topics. Okay, I'll be discussing very detailed idea about hydrogen spectrum. That time we'll come to know very clearly why you have this 2 over here, and you can see there some kind of formulas on the other side also. Okay, so Balmer gave a simple formula, that is 1 by lambda is equal to R into 1 divided by 2 square minus 1 divided by n square. Okay, where n is nothing but 3, 4, 5, etc. And you see here it starts with the 3. You will come to know why. Okay, why it starts with the 3. Okay, so where R is nothing but Rydberg constant. Okay, it is a constant which usually associated with the wave number. It has got a value of 1.0973 into 10 to the power 7 per meter. Okay. Now we will substitute this value over here. When you substitute this 3 on this Balmer formula, what do you have to get? Okay. So R value you already know, and 1 divided by 2 square minus, what is the value of n? N is equal to 3 square. Just do the calculation. Okay. After that you will get a value this much, 1.522 into 10 to the power 6. It is 1 by lambda. Just reverse it. Okay. Divided by 1 by this value. You will get a value which is 656.3 into 10 to the power minus 9, or you can write it as 656.3 nanometer. Okay. Have you find this wavelength anywhere? See, you can come here. See this, look at this. When the value is 3, you have the highest wavelength. Okay, this is the value of the wavelength, which is same thing. Okay. Now, when you substitute n is equal to infinity, what do you get? When you substitute n is equal to infinity, you can just make this term 0 over here. When you substitute, do the calculation, and you can see that you will be going to get a value 364. Okay. Where do you see this? See, 364.6. It is the same value what you see for h infinity. Okay. That's how these values were found. Okay. I have to tell you one more thing over here. I said you will get specific wavelengths in the emission spectra and absorption spectra. So there is a speciality that whatever spectra obtained, the wavelength value obtained for emission spectra, which will be the same as what you see the lines for the absorption spectra. So wavelengths are corresponding to each other in emission spectra as well as absorption spectra. Okay. So we will see the formula for the Lyman series and the Paston, Brackett and Fund series. Okay. So these are the next coming series. So we will discuss it later properly. We will just see the formula for that. You can see here. See, here we had 2 squared, but you can see that it is n squared. So this actually comes first in the spectrum. So I have mentioned in the first diagram, shortest wavelength which comes in the Lyman series. So it doesn't come under visible range. It comes in infrared region. Okay. Next comes Balmer series. Okay. And the third one, which is Paston series. Okay. You can see the formula for that. It is 3 square over here, and you look at the value of n. N is equal to 4, 5, 6. Similarly, the next one, fourth one, it is Brackett series. It comes under UV. Okay. So Paston and Brackett and other things comes the higher order of frequency. Okay. So see here, the value is 1 divided by lambda is equal to R into 1 by, it is 4. Look at the difference. 3, here 4. Then next comes the Fund series where it is 5. I'll tell you in the next topic why this is 1, this is 3, this is 4 and this is 5. Okay. And the R value is same for every series. Okay.